Good morning, students. Welcome to RSR International School. I am R. Mallikarjun Sharma, MSc MPhil. Today we are going to see Chapter 6, Work, Energy and Power. The prerequisites for this chapter are we have to know what is meant by a scalar product. Okay, it is defined as the scalar product between two vectors A and B is denoted as A bar or B bar. It is defined as the product of one of the component along the second vector and the magnitude of second vector. Okay, it is denoted with A bar or B bar. Okay, either A cos theta into B or A into B cos theta. Now differentiation. It is a differential of a function is denoted as d by dx of f of x. It is defined as limit f of x plus delta x minus f of x as delta x by delta x as delta x tends to 0. That is change in the function with respect to x when that change in x approaches 0. This is integration. That is, if you take the summation, it is over very small intervals. That is, the summation of elemental units is defined as integration. It is written as integral of f of x dx. Then you have to remember this one. Integral of k into x power n dx is equal to k times. This is k is a constant. X power n plus 1 by n plus 1. This is a basic one. Don't bother about things. Tension. This is, suppose if we are having a thread or a string. If we simply hold this one like this, then it simply hangs. But if we keep some or if we hang some weight to that string, then there is a force developed inside the string. That force developed inside the string is called as tension. T is equal to mg. Then if there is a circular motion, then the body executing the circular motion or curved part is going to experience a force called as centrifugal force. It is given by mv square by. You have to remember all these things. You come across these things in previous chapters, and you have to know about these mathematical details. Then we go to work. Okay, work is defined as the product of component of force in the direction of displacement and magnitude of the displacement. That is, by this one we can write like this: f into d cos theta, or simply it is a dot product of force and displacement. Okay, this is about work. Scientifically we define work like this. Then energy. It is nothing but capacity to do work. That is, if we are having capacity to do work, then we call that one as energy. Both work and energy are same, and for both work and energy, units are joule and dimensions are ml square t power minus 2. Then power. Power is the rate of doing work. It is work by time. How fast the work is going to be done is called as power. P average is written as total work divided by total time or instantaneous. That is, from point to point or from time to time is differential of work with respect to time, or the time rate differential of work is called as power. Then kinetic energy. If you take these different types of energies, first we get this one, kinetic energy. The energy by virtue of motion is called as kinetic energy. Okay, if your body is having motion, then we can say that some kinetic energy is there. This is given by k is equal to half mv square. Then potential energy. Potential means it is stored energy or virtue of the position or configuration. It is defined as virtue of position or configuration. It is stored inside the body. Suppose if you bring a body from ground to certain height, we are doing some work. That work is stored in the form of energy, or simply the work we are doing is going to be stored, and we call that one as potential energy. The gravitational potential. That is, for a body at height h, the potential energy is indicated with V, that is written as mgh. Similarly, potential energy for the case of a spring, where is given by half kx square, where k is called as spring force or spring constant kx square. For x displacement, we have to do this much of work. It is similar to same half m v square. Here, as we are doing against the displacement, it is half kx square. Now, work energy theorem. This work energy theorem. See, the change in kinetic energy is equal to the work done. Okay, whenever there is a change in the kinetic energy, there simply some work is done and they are going to be equated with each other. It is called as work energy theorem. Delta K is equal to W. Okay, the change in kinetic energy is equal to the work done by net forces acting on the particle. Then conservative force F is equal to minus dV by dx. See this from this potential, if the work done in moving a particle from initial point to final point is independent of path, then we call that one as that type of force as conservative force. If the work done depends on initial and final points only, then that type of force is called as conservative force, and the relation is F is equal to minus dV by dx, or we can simply write this one as delta V is equal to minus F dx. Then mechanical energy. The sum of potential and kinetic energies is called as mechanical energy. Then that is the sum of these potential energy and kinetic energy in mechanics. It is called as mechanical energy. Conservation. We know delta K is equal to work. Work is written as F dx. And the potential delta V is written as minus F dx. Then simply rearranging this one, we are going to get K plus Q, that is the total kinetic energy with the total mechanical energy is going to be constant. Okay, for a conservative, in the case of these conservative forces. Okay. Now we see conservation of energy for a body falling from height capital H. Okay, we just drop a body of mass m from this height H. Then we see three conditions. What is the energy at the topmost point while we are dropping, and what is the energy at some midway or midpoint between them, or in its journey, and what is the final energy while it is touching the ground? First, at height h, the potential energy is given by mgh. As it is at height h, the potential energy is mgh. As there is no velocity for the body, the kinetic energy is 0. Then the total energy becomes the potential energy there. Call it as equation 1. Then at height h, that is at a height h from the ground, that is it is displaced through a distance of capital H minus h. Okay. Then the potential energy is as height is small h, mgh. Then kinetic energy at this height is half your vh square, where vh is the velocity at this point. Now, using v square minus v square is equal to 2as, then substituting that value, this is final velocity vh square minus 0, it is starting from 0, is equal to 2 into, here acceleration is acceleration due to gravity g, and the displacement is h minus h, capital H minus small h. Then substituting this one for vh square, we are going to get g mg capital H minus mg small h. Mg small h, mg small h gets cancelled, and the total energy becomes mg capital H. Equation number 2. While reaching the ground, the final potential energy, as height is 0, then potential energy is 0. Kinetic energy half m v final square, where vf is the final velocity. Then again using v square minus v square is equal to 2as, we are going to get 2gh here. Then the energy becomes the total final energy becomes mg capital H. Equation number 2. That is, while it is falling at height h, it is having only potential energy, and at the time it is reaching the ground, its potential energy is converted into kinetic energy. Okay, that's all. throughout its journey. Now, as another example, we consider spring mass system. A spring with force constant K on one side is fixed to a rigid support, and on the other side a mass of M is attached to that one. Okay, and it is kept on a smooth horizontal plane. Now, if we move this one, then it is going to there is a force on the spring. Now, what is the work done on the spring? We are going to calculate, and we are going to have calculations for energy. Then we call this one as equilibrium position and this one as extreme position. That is, it is the maximum displacement. Now, at T, first we calculate the energy at maximum displacement T. The potential energy at maximum displacement is written as minus integral f dx. That is, it is going from 0 to xl. Then minus of minus becomes plus kx. Then we get half kx square. That is, the potential energy is half kx square, as maximum displacement is xl. Then the potential energy at this extreme position is, as it is going to stop and come back, its velocity is going to 0 here. That's why the velocity is 0, then kinetic energy is 0. Then total energy becomes the potential energy here. Now, at equilibrium position O, okay, the potential energy becomes 0 because there is no displacement, no potential energy. Then the kinetic energy is half m V O square. That is, the V O square here is displacing from this position to this position. Then again we are going to use v square minus v square is equal to 2a. If this is the final velocity minus initial velocity is 0, then 2 into a, 2 into a, for a acceleration is force by mass. But here the force is not constant. It is changing from point to point. The initial velocity, the initial force is 0 and the final force is, we are having some. That is, we have to take average. That's why we will get 2 in the denominator. 2 into m into the displacement is x. Then we are going to get half into m gets cancelled, 2 gets cancelled, f into f is k. See here. Here the force and the displacement, we are going from final position to extreme position to same direction. That's why we are going to get positive here. Half k x square. Then the total energy is this one. In this way, if we take this total energy here and the total energy here, both are same. The potential energy is converted into kinetic energy. Okay. This is how there is a conservation of energy in the case of spring mass system. Now, taking this conservation principle, we calculate the velocities at different positions for a body performing a circular loop. That is, a body moving in a circular loop. We can calculate the velocities at various positions by making use of this conservation of energy. For that one, we consider a particle of mass m tied to a string, and it is wheeled in a vertical circle. Call the velocity at the bottommost point as v0 and the topmost point as vc. Then, in general, the potential energy at the bottommost point is taken as 0. It is a reference one. Then, at A, we call this one a point A and the topmost point as C. At A, if we calculate the forces, tension is going to act towards the center. T minus mg, always mg is in the downward direction. That is equal to the centrifugal force, mv square by L, where L is the length of the string. Then this is the equation for force. Now energy at the bottommost point EA is equal to half m V0 square. Okay, where V0 is the energy at point E. Then we go to point C. At C, the tension is towards the center, and mg, it is also in the downward direction. T plus mc is equal to mvc square by L. Then, in order to just perform a circular motion, the tension slack at this position, that is, it becomes 0. Then mg is equal to m vc square by l. Then we get vc is equal to root gr. That is velocity at the minimum velocity at the topmost position should be vc is equal to root of gr. Then again we calculate the energy at point C. This is equal to half m vc square, where vc is the velocity, plus 2 into m into gr. This is at this position we are taking the potential energy as 0. 2m mg into 2l, 2mg. Then half m, this vc is substituting this value, we get gl plus 2 mgl, that is 5 by 2 mgl. Then this is the energy. Then equating this energy at point C to energy at point A, we get V naught is equal to root of pi g. See here, m into this is V naught is, we have to calculate V naught square. Equating these two terms, m get cancelled, 2 gets cancelled, then V naught square is equal to 5mgm. Then we get V naught is equal to root of pi g. This is the velocity at this position. Okay, at this position. Now similarly we can calculate the velocity at this one. See, we are going to get the same expression, half mgl plus, instead of 2gl here we are going to get mgl, that is 2 plus 1 3gl. We can get the value of velocity at point B as root of 3gl. These are the velocities at 3 points in order to have a circular motion. Now we see one-dimensional completely inelastic collisions. Collision is of two types: elastic collision and inelastic collision. In any collision, whether it is elastic or inelastic, it always going to follow law of conservation of momentum. If law of conservation of energy is also followed, then it is called as elastic. If it does not follow the conservation of energy, we call that one as completely inelastic collision. Okay. And now we see the case of the final velocity in the case of one-dimensional completely inelastic collision. Here we consider two masses with masses m1 and m2 with initial velocity for the first mass as v1i, and we consider the second mass initially at rest. Okay. Then for one-dimensional, theta1 is equal to theta2 is equal to 0. If we go to two dimensions, then we are going to have some angles here. Otherwise, we take this one. Then from the law of conservation of momentum, the initial momentum is m1 v1i. That is, for the first mass, velocity is 1i. This is equal to, after collision, in the case of inelastic collision, they are going to merge with each other. That's why we take m1 plus m2, and as they are merged together, only there is one final velocity. Then final velocity is this one. Then we can calculate the change of kinetic energy in this type of collision. Delta K is equal to, initially we are having this one, finally we are having this one. Initial minus final. Then instead of Vf, substituting this value, we are going to get this one, m1 square by m1 plus m2 whole square v1i square. Then this is all. I simply cancel it out. Then we are going to get half m1 m2 by m1 plus m2, which is the change of kinetic energy. Okay, we are going to get this one as a positive quantity. The next one is one-dimensional elastic collision. For this one, we are going to take theta 1 is equal to theta 2 is equal to 0. That is in only one direction. Then apply conservation theorem for the two bodies before and after collision. We are going to get m1 v1i, that is the momentum before collision. This is equal to m1 v1f. 1f is the v1f is the final velocity for the first body, plus m2 v2f. It is the final velocity for the second body. Equation number 1. Then applying conservation as it is elastic collision, conservation of energy, we are going to get m1 v1I square is equal to, that is cancelling out half. Then m1 v1f square plus m2 v2f square. Equation number 2. Then multiplying equation 1 with v2f and subtracting equation 2, that is in order to eliminate m2 factor, we are going to get this equation. Then simplifying this one, v2f into v1i minus v1f is equal to v1i square minus v1f square. That is where we are going to get v2f as v1i plus v1f. This is equation number 3. Then substituting this equation in equation 1, we get this one v1f. Okay, this is equal to m1 by m2 by m1 plus m2 into v1i. This is the known value. That is before collision we know these parameters. That is m1, v1i and m2 0. This velocity is 0. That is we know the 4 parameters. This is the unknown parameter after collision. This is we are getting this velocity in terms of known values. Then substituting this equation in this equation, we get v2f is equal to 2m1 by m1 plus m2 into v1. Okay, these are the values of the velocities after collision. Okay, in terms of known values. Now, similarly, we are going to go for two-dimensional collisions. Okay, then in general, these two-dimensional collisions we are taking up. Then, by applying conservation of momentum, we can get two equations. That is, see, this is the y direction, this is the x direction. Before collision, the momentum is m1 v1i for the first body. This is equal to m1 v1f. We have to consider x direction. That is, it is along x direction. It is v1f cos theta. m1 v1f cos theta plus this one m2 v2f cos theta. This is for the first body. Then for the second body it is at rest 0. Then the value after collision, that is the momentum value after collision, m1 v1f sin theta. If this is cos theta, this becomes sin theta. m1 v1f sin theta 1 minus, this is in this direction, it will be along this direction. Then m2 v2f sin theta. Then we are having two equations. Okay, and the unknown values or unknown parameters are final velocity of the first body, final velocity of the second body, angle with which the first body is moving after collision, angle with which the second body is moving after collision. 4 unknowns and 2 equations. Then, if we apply conservation of energy for elastic collisions, we can get one more equation. Then, that is applying conservation of energy of m1 v1i square is equal to half m1 v1f square plus half m1 m2 v2f square. Okay, we are going to get one more equation. By using the detector, we are going to find one of these two values, either theta 1 or theta 2. Then we can solve the problem. Okay, in this way we can deal the collisions easily. That is, we have to experimentally detect these values in order to know other parameters. Otherwise, we cannot solve. By making use of 3 equations, we can't get 4 unknown values. That's why by doing an experiment, we can have a solution for this one. Okay.